Okay, now in the last worksheet of today's session, we are trying to slowly develop some rules for integration. Now remember, in differentiation we came across lot of derivative rules. For example, if you differentiate a polynomial of this nature, you will get nx n minus 1, and if you differentiate sin x, you will get cosine x. Likewise, there were so many derivative rules for differentiation, and likewise there are some particular rules that we can apply for integration as well. Now here in this tutorial we are trying to develop one such important principle or a rule for integration. And for that particular purpose, the theory that we need is, if we have a function, if I name it as gx, which is the logarithm of fx, right? If we have a function like this, and if we are supposed to differentiate this one with respect to x, from differentiation theory we have already calculated that the derivative of this one is equal to f prime x over fx, right? For example, if we have gx as the logarithm of cosine x, then the derivative of gx is equal to f prime x. That means the derivative of this, which is negative sin x over cosine x. So this is a rule that we highly use in differentiation also, right? Let's see how can we relate this result to integration. Okay, right. Now what will happen if we have this sort of a function? If I name this one as negative sin x over cosine x, and what if we need to find the antiderivative of this simple f? That means, what if we need to find another big function, so that when you differentiate this one, you should get this as the answer. Now here there's an important thing that we have to identify, which is that this function is given as a quotient. That means with a numerator and a denominator, and there is a relationship between the numerator and the denominator. So what is the relationship? The derivative of the denominator is in the numerator. The derivative of this one is in the numerator. So if you have such a property, you can directly relate that one with the derivative of ln term. Okay, whenever you have a function in the denominator, and if you have the derivative of this denominator in the numerator, you can at once relate this to the derivative of ln fx. Okay, in other words, this piece of function is the antiderivative of this whole thing, because that goes with the definition. What do we mean by the antiderivative? We need to find a capital F, so that when you differentiate the capital F, you should get the initial function as the answer. So when you differentiate this one, you will get this as the answer. So the antiderivative of this one is equal to this function. So all these things based on the derivative of ln fx. And if we further try to, like, if we increase this function a little bit, if we change this function a little bit, how about if we have simple fx as sine x over cosine x? What is the antiderivative of this one? Now here we can see that the derivative of the denominator is not exactly written in the numerator, but still you can do some simple rearrangement so that you will get the derivative as the answer. I mean the derivative of the denominator. If you can get the derivative of the denominator when you have a fraction, then it is very, like, it will behave very nicely because we have this property in differentiation. So whenever it is possible to rearrange the terms so that the derivative of the denominator appears in the numerator, then it's a very suitable method. So now even in this new function we can do some simple rearrangement and obtain the derivative of the denominator. So in this case, if we differentiate ln cos x, you will get this one as the answer. But the only difference here with the previously discussed question is you should have an additional negative sign in front. Okay, so in other words, if we write capital F as negative ln cosine x, then see what will happen if you differentiate the capital F. When you differentiate capital F, you can consider negative as a multiplication with a constant so that you can take it out when you are differentiating. So you can take the constant out from the derivative and then you will end up with the derivative of ln cos x. That means the derivative of ln fx, which is the f prime x divided by fx. Now in this case our fx is cos x, so cos x negative sine x, and this negative along with this one will cancels out and give you the result sine x divided by the cos x, which is our original answer. In other words, capital Fx is an antiderivative. You don't call it as the antiderivative because it is not the only possible answer. You call it as an antiderivative, not the antiderivative. Okay. So, and in this third worksheet, you are asked to find a particular antiderivative. You just have to find one antiderivative. You don't have to mention it as a general with an arbitrary constant. Okay. So, roughly speaking, if they have just asked you to find the antiderivatives, you just write this as negative ln cos x plus c. But if you are supposed to find a particular one, you can just substitute any value instead of c. Now say for example, if I substitute 1, you can have fx is equal to ln minus ln cos x plus 1 as the antiderivative. So no matter what value you choose for c, it can be 0 or it can even be a negative number. You will still get this one as the antiderivative with the suitable, with the chosen c value. Okay. Now for simplicity, if we choose c is equal to 0, then you can write fx, capital Fx, equal to ln cos x plus 0 as a particular antiderivative that goes with c equals 0. Now let's move to this question, that is part A of the third worksheet. Here again we have to find a particular antiderivative and we are given with a fraction. Now as you have a fraction, we should first check whether we have this relationship, that is whether we have the derivative of the denominator in the numerator. So when you differentiate the denominator, we can see that they have directly given the derivative of the denominator as the numerator. So we can just write down this one as the derivative of ln x cubed minus 5x plus 12. The derivative of this thing is equal to this one. So we can directly write down the antiderivative. We can extract out an antiderivative as this one. In other words, if we differentiate capital Fx, you will get simple gx, where capital Fx is equal to ln this term. And this is not the only antiderivative we have. We have everything added with a constant c, ln this one. If you add an arbitrary constant here, it will still give out an antiderivative. But if you are supposed to find a particular antiderivative, you can just substitute a particular value instead of c. Now for the sake of convenience, I am substituting 0. So you will get a particular antiderivative as ln x cubed minus 5x plus 12 as the particular antiderivative. Finally, let's move to this question. This one is a bit tricky because at once, if you observe whether you have the relationship f prime over f prime, it is not there. But the trick here is to understand this given function in terms of two ln functions. Now, if you have, I'll explain it in a different way. If you have logarithm of fy, now instead of x variables as it was in the previous questions, we are using y. So we should differentiate everything now with respect to y. Okay. If we have a function in terms of y, and if it is inside a logarithm, and if you need to differentiate this function, what you will get is f prime over y divided by fy. Okay. Now let's say our fy is equal to ln y. So that means when we differentiate this given situation, in other words, if we differentiate ln of ln y, now here instead of fy I am writing ln y because a function of fy will also allows it to be ln y. Okay, it can be any other function, but also it will allow this one as well. So instead of fy, I am writing ln y. And then according to the derivative rule, we will get f prime over y divided by fy. And what is f prime y? That is 1 over y. The derivative of ln y is 1 over y. The derivative of ln x is 1 over x. So whatever the variable you use here, if you are differentiating with respect to the same variable, you will get the same results. Otherwise, if you have two different variables, you will have to use chain rule. Okay, but that has nothing to do with this one, because we are differentiating with the given with respect to the given variables. Okay, so here you will get 1 over y. That means in the numerator you will have a 1 over y term, and in the denominator you have fy. That means ln y, which gives you y 1 divided by y times ln y, which is the original function that they have given. Now we are asked to find the antiderivative, and we have found a function so that when you differentiate this capital F, you get this as the answer. In other words, capital F is the antiderivative of simple zy. Now these type of techniques come with the practice. So at once you may not be able to identify the suitable antiderivative, but still these are some very good examples that you should have practice with. Especially in exams, they might test your knowledge in these sort of calculations. So please be familiar with these types of antiderivatives, and let's meet on next Thursday.